Now we'll take a look at using circular motion to describe orbits, and specifically geosynchronous or geostationary orbits. So geostationary orbit is just an orbit where something that's in orbit around the Earth is always pointing up over the same point. So you can imagine for a satellite this is important, because if you're located here, you want the satellite to always be in the same position. You don't want it to be moving, so that eventually sometime later, it's the satellite's over here and it's gotten a bit ahead of you, so now you don't have a direct line of sight to the satellite. So what we have is you have a satellite. We know that there's a force of gravity from the Earth to the satellite, and also the same magnitude force of gravity from the satellite to the Earth, right? But if the satellite's moving, then it's traveling at a velocity v around this orbit. And because the Earth is turning at roughly a constant velocity, constant angular speed, we also want the satellite to be traveling at a constant velocity. So to find that, we'll just write our net forces. So we'll look at the satellite, and so we know that the force is just the force of gravity, which is mass of the satellite minus mass of the satellite, mass of the Earth, g, over r squared, where r is just the distance from the center of the Earth to the satellite in the orbit, and this is equal to the mass of the satellite times its acceleration. Of course, this is in the r hat direction. So in this case, in the case when it's directly above us, it's just y hat. Right? Well, we know that the acceleration a is just v squared over r, and we can cancel out the mass of the satellite. So we see that the mass of the Earth, g, over the distance between them squared, is equal to v squared over r. But of course, we don't necessarily know what the velocity of the satellite is either. And so let's say, in this case, there's really two unknowns. We don't know r, and this should be a lowercase r over here because this is the same radius. So we don't know r, and we don't know the velocity. So we can really choose which one we want to solve for, and solve for either one. Okay. So in the first case, let's say we want to find out what the radius is. And so, in other words, if we want a satellite in geostationary orbit, we see that it doesn't depend on the mass at all. It only depends on the velocity. And the velocity is given, right? Because we know we have a constant velocity, and it's going to be the change in distance, which is 2 pi r, over the change in time, t, which is the period of one orbit. Well, we know the period of the Earth going around in a day is 24 hours. So we can write that what we have, that the acceleration is 2 pi r squared over the period times r. And so then multiplying by r squared and dividing by 4 pi squared, we have MEG, and multiplying by t, divided by 4 pi squared is equal to r cubed. So the radius is the period, mass of the Earth, g, divided by 4 pi squared to the 1/3. And so this is the radius for a geostationary orbit. This is the only radius that you can get for a geostationary orbit. So we really have kind of a finite number of satellites that we can put in an orbit like this around the equator. Okay. But now let's say instead we had wanted to solve for the velocity, right? Because we can do that too. Instead, now we just have to change this equation and write that r is equal to the period times the velocity over 2 pi. So we go back to this equation and we can cross out one of the r's. So we see that we have mass of the Earth, g, divided by the period, v, over 2 pi is equal to the velocity squared. So multiplying by another velocity, we see that the velocity cubed is going to be 2 pi mass of the Earth, g, over 24 hours. So the velocity of a geosynchronous orbit is going to be the cube root of 2 pi mass of the Earth, g, over t, the period. And again, this is the mass of the Earth, this is g, and t is 24 hours. So this also gives us the velocity of a satellite in geostationary orbit. And so quickly, I guess we can briefly mention that we can still check the units. So we recall that this term here is g. So this is an acceleration. So we know, because that way we don't have to worry about what the units of Newton's constant are. We know that this has units of meters per second squared. And so just MEG, or I'm sorry, ME big G is going to have units of meters cubed per second squared. So we have a meters cubed per second squared. Divide by a second is meters cubed per seconds cubed. And then you take the cube root of that, and that gives you meters per second. So that's fine. And then we check the radius. Again, we have meters cubed per second squared multiplied. Let's see. So yeah, meters cubed per second squared. We multiply by a meters. Let's see. Oh, so here we see that I left off a squared on the period here. I'm sorry, that's fine for v, but when I squared it, I forgot to square the period before, which means it should also be squared. So now we have a meters cubed per second squared times second squared, so it's just meters cubed, and then we take the cube root and get r. So now you even notice myself that I caught a mistake, and I found it just by checking the units. And so now we see that the units are right, and that these answers make sense.